it's for what I do. And yeah, that is the first page. I forgot that was the first page. Okay, just going through record here. Meg, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay.
I just switched.
Yeah, no, that's okay. I just counted because it's quicker. We're all here. Of course, I marked Maggie here because I was. Yeah. Anyway, that's not what I see. This could be a sign of a problem then.
Because there is no.
All right, Plan B. Plan B. Okay. See what I see.
I wasn't clear on that. Well,
That's what I see. Okay. Last time we saw each other, you were taking the exam. She is photocopying the exams now, and so they'll be here well before we get out of class, so you can have them back. Hopefully the scores are good. I looked at the Scantron scores, and they were quite nice. That makes me happy as a teacher. I haven't looked at anyone's individual score except for Satish. Okay, moving on. We still haven't finished talking about the evolutionary pathway for a star. So this graphic, which is an extremely busy graphic, is laying out how we believe stars, not this one, the next one, how stars live and die. So we can't see a star go through its lifetime. Star lifetimes, we believe, are very long compared to human lifetimes. So all we can do is observe different stars at different stages in their life and try to figure out what's going on from those observations and from making computer models of the physics that we understand from here on Earth. So here's the graphic I was thinking was up there. There you can see it's very busy. So it starts with the ultimate force in astronomy, gravity. Gravity is what's holding the star together. And gravity is crushing the star, making it have a high pressure in the center. And that center, as you crush it and increase the pressure, you're also increasing the temperature. And when the temperature in that core reaches a high enough temperature, then you have fusion begin. Fusion, as we've already studied. That fusion releases a lot of energy. Releases a lot of energy, makes it hot, and that high temperature increases the pressure. Pressure then is pushing out because of the high temperatures, and we have a balance everywhere in the star called a hydrostatic balance, where we have the pressure pushing out and the force of gravity pulling in, and those are balanced everywhere to have a nice stable star, one that's not collapsing or blowing up. And then the star will continue like that until it runs out of fuel. Its fuel, since it's fusing hydrogen to helium, is hydrogen. When it runs out of hydrogen to fuse, then the reaction, the core slows down. It isn't producing energy as quickly. If it's not producing energy as quickly, then it cools down. The pressure pushing out gets smaller. Gravity pulls stuff in. Of course, as gravity pulls stuff in, that raises the temperature up again. And so it gets hotter again there in the core, and then depending on the size, you may have different things occur. Eventually, when all is said and done, the end point for a star depends on its mass. If its mass is small enough, it'll be a white dwarf. Our sun's mass is reasonably small. We believe it will easily end up as a white dwarf. If its mass is larger, it could end up as either a neutron star or a black hole. So that's the basic story of the life of a star. Now, got two graphics that were shown by the group presentation for the actual life cycle. So you've already seen these once. We start with a cloud of gas. We actually call this cloud of gas by a special name. It's called a molecular cloud. Now, a cloud is a nebula. That is a correct term. Okay, but this has the special name of a molecular cloud. What that means is that the temperature is low enough that you can form molecules of hydrogen instead of having atoms of hydrogen hanging out. So the temperature there is somewhere in the ballpark of 10 kelvins or so. 7 to 15 kelvins is what I wrote on a later slide. So you have this big cloud of gas. And then something has to happen to make that cloud start collapsing. And we will deal with the scientific theories on what could possibly make it start collapsing a little bit later. But as it collapses, the space between atoms gets smaller. And as the space gets smaller, what happens to the force of gravity?
It exponentially gets greater.
It gets bigger. And so then the force pulling together gets bigger, and that starts taking over and makes it collapse. Because of rotation, if you have your arms out and you spin slowly, what's going to happen to your rotation when you pull your arms in?
Go faster.
You go faster for conservation of angular momentum. So as you have this big cloud and things shrink in, it spins a lot faster. And as it spins, it tends to form a flat disk, and you have material that's getting pulled in that then gets redirected out to make these things that are called bipolar flows. So it's not material coming from the protostar. It's material that was being pulled in that got redirected outward because of electromagnetic forces. Well, it continues to collapse and it becomes a star, such as our sun. This shows our sun today because our sun is a low-mass star. When it runs out of fuel, I talked about, well, the core is going to have to collapse because you don't have as much pressure pushing out. But we have a number of things that go on to actually make the star expand when it runs out of fuel. That kind of doesn't make sense. But it expands when it runs out of fuel. As it expands, if you take a gas and you let it expand, it naturally cools. It's the way of thermodynamics. And so your star becomes cooler, hence the color shifts toward a cooler color from whitish to reddish, and it becomes larger, so it becomes giant, and we call it a red giant. Now this stage here, the yellow giant, is a special stage where it reaches a new equilibrium, and we have to look more in the details to see what's going on there. Eventually it runs out of all fuels, becomes another red giant, and then it forms this nice planetary nebula. Now notice the size of this planetary nebula, one light year across. It's pretty big, right? Material, this nebula is gas that was pushed off by the star while it was dying. So while it was in the giant stages, it was blowing off a lot more mass. Now you've already had a homework problem that dealt with the mass being blown off of the sun. And so we know the sun is blowing off mass right now, but it's a small percentage of its mass. During these death stages, the amount of mass that's being blown off becomes much more significant. So the star may blow off as much as half of its mass during those death stages. So there's a lot of gas that gets blown out there in the end. And then when it dies, it sends out a shock wave that excites the electrons in the gas. They de-excite and give off light. That's called a planetary nebula. It has nothing whatsoever to do with planets. It's called planetary nebula because the colors are similar to the colors of Uranus and Neptune. And so they said, ooh, that looks pretty colors like some of the planets, and they called them planetary nebulae. Nebulae is plural of nebula, and it just means cloud. And then you end up with a white dwarf that's 1/100th the size of the sun. A tiny little core of what's left. Now that's a low-mass star. Let's look at the same picture for a high-mass star. High-mass star, interstellar cloud looks the same. The fact is, a single interstellar cloud will make many, many stars all at once. So, of course, it looks the same because the same cloud could be making a small mass star and a big mass star all at the same time. Forms the protostar that looks once again the same. The massive star, the only difference for the massive star is instead of looking kind of yellowish, this one looks more bluish. Why would it look more bluish? Hotter, exactly. Goes through a pulsating yellow stage, a little bit different. Becomes a red giant, well, that's the same. Then becomes a supernova. Notice the size there. How's the size of that supernova compared to the size? 10 times bigger than a planetary nebula. And then you have either a neutron star or a black hole remaining. The neutron star, smaller than the white dwarf. Black hole, smaller. So we're talking small results for the biggest things. Of course, you gave off a lot of gas, and that's what this supernova that lights up is. It's once again gas that was given off during its death stages. Now, one more little picture before I have my first clicker question. This here is showing, what do we call this diagram here? HR, or Hertzsprung-Russell diagram. And it's showing how the formation and death of stars appears on an HR diagram. So the yellow line is the small mass lifeline. Time would be measured starting, here is early, okay, ear, see that ear? And this would be, that's early as well.
Could you use something like a fluorescent green?
I thought the blue was outstanding, but apparently not. I'll use white again.
Not with this projector.
So here, this edge here is early in the life stage. So they both start coming in from that point. And then they're aging as you go following the arrows. You can see there are arrows here going like this. So if you look at these, you see a story that you can read. That is, it starts way off on the right. Where do you suppose it would go from here? What direction would it go from here? It would go for going backward in time. If we went backward in time, so forward in time it goes this way, so where would it go backward in time? Would it go up or down? Down. So it started somewhere out here. Really cold and not very luminous, right? Because cold temperatures are on this side. So way out here, really cold. What temperature did I say it started at? Starts in a molecular cloud, which has temperature of somewhere around 10 kelvins. So it starts way out here at around 10 kelvins, and its luminosity is nil. But then as it starts compressing, it starts giving off more radiation, and it comes up, and the temperature goes up. The small star comes in, comes down here, and it's on the main sequence. It burns across the main sequence, so the main sequence is going basically from there to there. It's not a single point. The main sequence is the region it burns across during 90% of its lifetime. So time is not linear with that line. 90% is just between those two lines I drew. And then when it comes off, it goes through some interesting little jags up here. You notice you have yellow giant stage and red giant stage. So you can see it hit red giant here and hit red giant again out there. And then it goes through the planetary nebula, short-lived compared to the rest of its lifetime. Then comes down here to the white dwarf. The more massive star comes straight across without much of that interesting stuff, burns across the main sequence up here, so that's 90% of its lifetime. Then it comes up here and the supernova is the end. There is no continuation at that point because it done blown up.
Word.
Yeah, I'm good at this language thing. We use English.
So at that point, if we were to continue following that blue line, it would just drop completely. At that point.
At that point, it would, if it's a neutron star, it's going to drop quite a bit, and you would, right, because it's not nearly as big, so it's giving out a very small amount of light. So I just go, and it gets super hot. If it's a black hole, it's completely gone. Okay, we are open for answering questions here. How do scientists, quote, know, end quote, that the life sequence of a star that I've just shown you in these preceding 3 graphs is correct? That it's truthful? Okay.
Neither do I.
Okay.
Wow.
Eliezer, are you click a list as well?
I'll click, but I'm still trying to make up what my mind does.
Okay. 10 out of 10 people, and I'm going to change the color away from white. 10 out of 10 said C. Now, that's the correct answer. Looking at these, what we would like, ideally, for scientific theory is to be able to reproduce it in the laboratory, right? Well, we can't do this.
What's the big deal? It's just a star.
Yeah. So we can't do that. That's not possible. So we have to go, what else would we like to do? We would like to then, we have a hypothesis that's based on scientific ideas that explains what we see. What do we see? We see light. And from that light, we then say, ooh, that must be an object. And that we look at details of light and try to get more information about it. That's what we see. That's our pure data. And then we say that light must have been produced by the whole story I gave you. That comes from taking the observed thing we had in our existing science and putting them together to come up with an explanation that could explain how it works. Of course, nobody can say, oh, yes, that's the right one. If you were to ask somebody 120 years ago, what's the life cycle of a star, you probably would have got the slack-jawed, what are you talking about? It's a star. It's there. It's always been there. It'll always be there. Why are you asking these questions? That's what was understood, basically, at that point. You ask them, where's the energy come from? Maybe it's burning. It's got some wood in there. I don't know. Right? There was not even any idea of how fusion could occur 120 years ago.
Magic.
Yeah, magic. Given that 120 years ago, there was no clue as to how the sun could exist, how it could produce this energy, it's easy to understand how people who believe in the wisdom of man would look at me, who believes in a creator, and mock me for saying things about God creating this stuff. Because 120 years ago, that would have been, well, we have no answer, so we appeal to a higher authority. Now science has an answer, and we don't appeal to a higher authority on something like this because it appears fairly straightforward. But then we talk about how the universe come into existence. How did life come into existence? Science doesn't have a good answer for that. But now they say, I'm a simpleton by appealing to a higher authority, saying that God created life. So you can see how people would come to that way of viewing. I hope I've made it clear. I believe that God created life in the universe. This top one, because theory says it must be true. If that's all I taught you, if I showed you that life sequence of a sun or of a star and said that's the way it is and stopped there, I wouldn't be teaching you. What would I be doing?
You would just be showing you.
I'd be indoctrinating you. I'd just be telling you, here it is, believe it. It's the way, we know. That's not the way science is. Science is not about telling people what to believe. It's about trying to give them the evidence so they can figure it out and have it make sense. So we're going to go through and try to see the evidence, try to make some sense out of this. So start with that molecular cloud. You have the molecular cloud and you have to have something make it start collapsing. Notice we have those little magenta arrows to indicate stuff is randomly swirling around. And the random swirling is always going to have a net non-zero swirl, right? Chances of having a net absolutely zero is virtually zero. So it's going to have a net non-zero swirl just by random chance. And as it collapses, that gets amplified because of bringing the mass in. So that's how we get the rotation and get those jets. So when we get to this stage where it's collapsed and we have those jets, we call it a protostar. Right? It's a prototype of a star. So this here, once again, we're talking about a theory, right? So in our scientific method, it makes predictions that we're going to have this protostar that has the jets around a gas-enclosed protostar. So then the scientific method says we're going to make a test. So we're going to go and do the only kind of test we can do. We're going to use our telescopes to look and see if we can find the objects predicted. Right? So we predict should have this kind of size, temperature, etc. And then we go looking to see if we can find things that fit that prediction. And as luck would have it, well, this is the graphic on the molecular cloud. Molecular clouds, you have to have that cool temperature for the cloud to be able to collapse and form stars. And they contain somewhere between around 10,000 solar masses, a mass of 10,000 suns, to 1 million solar masses. And this nice low temperature, the density is only about 100 to 300 molecules per square or cubic centimeter. So a cubic centimeter, that big. 100 to 300 molecules in that. Normally we have billions in that space. Billions times billions in that space. So it's very, very rarefied, as we say in science. The molecules are rare, even though that seems like a big number. Okay, now to the pictures of protostars. This here, the pillars of creation, as it's called, has things like this right here that I pointed out during the student presentation. That, do you remember what I called it? It's the Eagle Nebula. And that is called an egg. An evaporating gaseous globule. Why is it called that? Because it's kind of cute to have the Eagle Nebula have eggs in it. Okay? That is matching predictions of what should happen when a star forms. You have this big, multiple light years long pillar, and a protostar has formed out there, and radiation pressure has pushed the gas of the pillar away, but we're left with a little trail that's kind of been blocked by that protostar, and that's why that's why you see the little trail behind it. So when scientists look at this, they say, wow, we see the evidence that matches the prediction of the model. And since we see the evidence that matches the prediction of the model, then we have a test that gives us a little more confidence. Now, have we proven the model correct yet? I say model all the time here. Model is a framework for thinking. Hypothesis is the early guess. The theory is when you short things up a bit. Just put it all together and not worry about the terms. Have we proven anything correct here?
No, not proven.
Okay, so what have we accomplished then?
We've established that there's evidence for a theory.
Okay, we have established that we find a prediction of the hypothesis. And so we have reason to believe, hey, maybe this wasn't just off the wall, maybe there's something to it. And that's as good as we get in science, frankly. You can get more and more confident, but you're never going to prove it right. You're never going to have the evidence that says, oh yes, this is the way it is. You could just have an experiment that says, nope, it's not that way. And so you start gaining confidence if you find more evidence that backs it up, even though it doesn't prove it. Here are some pictures. Now, these are infrared. Invisible light, they're just dark things because we can't see through the gaseous cloud. But in infrared, we can see through the gaseous cloud. That means that these are false color images. They generally put red in the middle because red means cooler temperature, and these are cool compared to stars. But we have pictures here of objects that match the prediction of protostar. So, we have reason now to suspect it's correct. Here's a picture, and you can clearly see on this picture the bipolar jets. One that's going out like this, one that's going out like this. You see this thing out here, and you see something that looks like that there. Those are actually shock waves from the bipolar jet hitting the gas that was already out there. And so it kind of helps you to see the jet by seeing those as well. So these are matching the idea of the protostar. Once you get the core to 1,000,000 kelvins, then you'll start having some fusion. It's not going to be self-sustaining fusion in a star at this point, but you'll have some fusion. That is some conversion of mass into energy following that proton-proton chain that we talked about. So now all of a sudden you've started producing energy. That is, it's not making energy, but it's converting and releasing it. And so then it will start blowing stuff away and clearing away the shroud so you can start to see it. And when it gets hot enough in the core for fusion to begin, that's when it truly becomes a star. When fusion begins, it goes from being a protostar to a star, when fusion in the core begins. And like I said, it clears away the atmosphere and you can see things. Now the thing I want you to notice on this graph is the time. We have birth lines. These different colors are different colors, they're all the same color. The red lines, the different lines, are showing stars of different mass. High solar mass, or high masses, 15 solar masses, comes in up here, makes a very hot star. Low masses coming down here make cool stars. That kind of makes sense to me. But the thing that's more important for me to note on this is the times. What forms a star quicker, a massive or a low mass star? What becomes a star quicker? What gets to the main sequence quicker? Yeah, the other one, the high mass. Notice the low mass stars, if you get to being 1.5 solar masses, it takes about 10 to the 7th or 10 million years to become a star. From the beginning of the cloud starting to collapse until it becomes a star. If you have a mass that's about 5 solar masses, it only takes 1,000,000 years, 1/10 as long. So you only increase the mass by about 3 times, and it takes 1/10 as long. And if you get up there to 15 solar masses, it's going to form a star in like 100,000 or less years. So the time it takes from beginning to form a star is much shorter for more massive stars, much longer for smaller stars. How do we know this?
Aliens.
The aliens told us. Good answer, but not right one.
Is it because we observe that there are more
it's going on the path faster. And so if we can see that, okay, this star looked like this at this 200 years ago or 300 years ago, it was observed like this, and now we see that it's slightly different in this way, then we can say that it has moved so many inches along the path of reflection that we predict.
Now that is a good thought, although we do have to keep in mind even 200 years, which is kind of optimistic for us putting something on an HR diagram that's from 200 years ago, right? Because we didn't have very good observations. Yeah. But even 200 years compared to 100,000 years is but a blink. So there's not much to that, but we've talked about clusters. The reason we didn't start doing the lab final until, 3 weeks ago or whatever, is because I wanted you to be able to point out the Subaru constellation. Well, it's not constellation, it's an open cluster. Otherwise known as, what were the other names for Subaru? The Pleiades, the Seven Sisters. That's an open cluster. It's a cluster of stars that were all formed at the same time from the same molecular cloud. And so all of the stars in the Pleiades are all essentially the same age. And so we look there and we look at all of the stars in the Pleiades and we plot them on an HR diagram. And then what we're looking at is the HR diagram for stars that are this old. And we look at other clusters of stars and we plot their stars on an HR diagram. And we can start plotting out where stars fall on an HR diagram at different ages. And that allows us to see, oh, the first stars to form, if you have a young cluster, you find that you have bigger stars. An old cluster, you have smaller stars. That tells us that the old ones must have formed later and lived longer. The young ones formed earlier and died earlier. Young ones, excuse me. I said young and old for the massive stars formed earlier and died earlier. The low mass stars formed later and died later. In fact, the scientific interpretation of the data you had on the test here is that, well, there are two answers. Number one is low mass stars have much longer lifetimes than large mass stars. So you might think of it like this. Let's say that there are 100 people born every year. And of those 100 people, 1% are born extremely intelligent, but they die by the age of 5. And 80% are born, room temperature intelligence, but they live to be 100 years. And so if you just go do a random sampling of people, what are you going to find the most of? Room temperature IQs, because A, they're the most formed, and they live the longest, so they're going to dominate the population. That's the second one. The second reason is the stars form of all different masses, but the smaller they are, the more likely. So smaller stars are more likely to be formed, and they have longer lifetimes. So those are the two reasons scientists have for that explanation of the data. That was, it was very clear. You had way more M's than anything else. And that's their explanations. All right. The masses of stars. The lowest mass that, according to our theories, can form a star is 0.08 solar masses. That is 8% of the sun's mass is the lightest you can have a star. Anything with less mass, it doesn't have enough temperature produced in the core to have a nice sustained hydrogen fusion. And so it kind of fades away from 0.016, that's 1.6% of the sun's mass, to 0.08, 8% of the sun's mass. Those kind of fall between the definition of a planet and a star. And so those things are called brown dwarfs. Brown dwarfs aren't stars. They're like superplanets. Superplanets are substars. Right? They're in between. Now Jupiter is a little bit smaller than that 0.016. So Jupiter is not a star and it's not a brown dwarf. It's just a planet. But if Jupiter was, I think it's like somewhere 80 times more massive, we would have 2 stars in our solar system.
So we would have a binary.
Yeah, we'd have a binary system there. So you can see how binaries form. We had things clumping together, and Jupiter just didn't get enough clumps to be a star.
That's fascinating.
Questions, sir? Now, there's also a maximum size, 150 solar masses. Anything bigger than that, and it can't be stable. You have so much pressure pushing out that it can't collect stuff, and so you just have a limit of stars between A and B. Most massive stars, 150 solar masses. Most massive stars, very short lifetimes. They burn very bright and then they're gone. Much like people will say about Hollywood starlets, She burned bright and now she's gone. Who are we talking about? Goodbye, Norma Jean. Okay, you guys. Another question for you. What is the minimum mass of a star? Very good, Sarah.
Was she the first one?
Yes, she was the first one. That's how I know it was her. The guy.
I will beat you one day.
The second person was right, too. The third person was wrong. I don't know who was whom, except for Sarah was first. Okay. That's right, Kib said you didn't have us. So this time we had 2, 5, 3. All right. Of these numbers, we talked about 2 of them. What 2 numbers did we talk about?
0.08.
0.08 and 0.016.
Yeah.
And, by the way, 0.016 is not 2 times. Yeah. What was the significance of 0.016 solar masses? Well, the brown dwarf is between those 2 numbers. Below 0.016, planet. Above 0.08, star. And in between, we have that brown dwarf that's not a star, so minimum mass for star, the brown dwarf doesn't fit. But it's not a planet either. It's that tweener. And I am very glad no one answered this one. That would deny the starhood of our sun. Okay. Here we get to why. Why does it take longer for low mass stars to form? Right? I told you we have actual observations of a bunch of stars all the same age, and that's where we can see that indeed lower mass stars take a longer time to form. But science, we want to explain why, and so here's our reasons why. It has a smaller gravity, which means that it doesn't pull stuff in as quickly. And it doesn't create as high of a pressure. In order to get the temperatures necessary for fusion, you actually have to compress the core a lot more, because you don't have as much mass to create that high temperature. And so you end up having to really crush these things down. It takes a long time to do that. And you just barely get it crushed enough to start fusion. So the fusion goes at a very low rate. That's why they live a long time. High mass stars, you have such a high gravity that they very rapidly get crushed, and they easily reach high temperatures in the core, which produces a very fast fusion and a short lifetime. Short time to form, comes right in, because high mass, high gravity. Okay, this one here, you better all get. If you don't get this, you probably didn't do well in the test last week. Okay, week and 3 days ago, whatever. What produces the heat in the star? And if I said 120 years ago, you just would have said, I don't know.
You would have had to include something on there where you magic.
Well, I did have combustion. Combustion is burning. Nobody said it's burning. That's good. 9 people said it's the fusion of hydrogen into helium. As one person said for her reason, because the song says so.
Fair enough.
That's what I said. One person said nuclear fission. What is the difference between fusion and fission?
It's the difference between tearing something about and smashing something together.
Okay. Sarah was doing it with her fingers. You're saying the words. Fusion is when 2 become 1. Fission is when 1 becomes 2. And fusion releases a lot more energy than fission. So it's good that our sun is working on fusion. It releases a lot more energy. And in fact, once the first fission bombs were created, people said, well, golly, if we made a fusion bomb, we could have a much more powerful bomb in the same size.
We could really kill them.
That's right. And it makes me a little bit happy that the person who led the project said, no, I'm done with bomb making. And so they had to find other people to lead the project because he had already made something horrible. Yeah.
What about the stars that are cooler and don't have hydrogen and helium in them?
Well, all stars have hydrogen and helium. The amounts might vary, but they all do. That's not what you meant. Stars that are very massive in their dying stages will be fusing something besides hydrogen and helium. They still have hydrogen and helium as their dominant materials, but they're fusing other things because they don't have enough of those to have efficient fusion of hydrogen and helium. But they're still fusing. They're fusing larger things.
Just eliminated saying that they have hydrogen and helium, even though they still
Yeah, that's right. We say that it's out. It just doesn't have enough. It's kind of like saying, is your gas tank no drops of gasoline? No. It's just not getting enough gasoline in that little fill pipe. It's pulling as much air as it is gasoline, and you say, I'm out of gas. Okay, I have finished a lot less than I planned. What happens if you have a more massive star than our sun? If you have a star that's maybe 50% more massive than our sun, it will get the core hot enough to make fusion occur a different way. Now, we studied that proton-proton sequence reasonably carefully. And now we say for more massive stars, where it gets up to be more than 20 million kelvins in the core, there is a more efficient way of fusion. And that more efficient way requires that you have some larger elements. Well, we've just been seeing hydrogen and helium. There are trace amounts of these other things. And this more efficient method is called the CNO cycle, carbon, nitrogen, oxygen. The CNO cycle is a cycle where you add a proton to a carbon atom. And so you take it from a carbon 12, you see the top there is a carbon 12. The 12 means it has 12 things in the nucleus. 6 protons if it's a carbon. So carbon 12 is 6 protons, and 12 minus 6 is 6 neutrons. You add a proton to it, and now it has 13 protons in the nucleus. So it becomes nitrogen, because nitrogen means 13 protons in the nucleus. It's nitrogen 13, or nitrogen means 7 protons in the nucleus. Wow, I said that wrong. Nitrogen means 7 protons in the nucleus. It's nitrogen 13 because it has 6 neutrons, 7 protons, 13 total nucleons. Well, this nitrogen 13 isn't stable. It undergoes a decay where it gives off a positron. Positron, anti-electron. We saw that in the proton-proton chain. So we saw these coming off in the proton-proton chain. That was a good circle. When that occurs, what happened in the nucleus is one of those protons was destroyed and a neutron was created. So it changed from having 7 protons and 6 neutrons to having 6 protons and 7 neutrons in the nucleus. Still 13, but now it's only 6 protons, so it's back to carbon. That carbon 13 gets another proton and becomes a nitrogen 14. Nitrogen 14 is stable. That's the nitrogen that we're breathing right now. You guys know 79% of our air is nitrogen, right? And that nitrogen is molecular nitrogen, so it's 2 nitrogen atoms, 2 nitrogen 14s, that are bonded together. That nitrogen 14 then, so we've gone from the C, the carbon part, to the N, the nitrogen part, because we have a stable nitrogen. It gets hit by another proton. And that proton makes it now have 8 protons in the nucleus. That's oxygen. So now it has 8 protons, 7 neutrons, oxygen 15. Oxygen 15, once again unstable, goes through the same particle interaction where it gives off the positron, the neutrino, and destroys a proton and makes a neutron. So it returns to nitrogen, but now it's nitrogen 15, absorbs another proton, and that becomes oxygen 16. Actually, I said absorbs another, well, it does. It becomes oxygen 16. But the oxygen 16 actually doesn't stay as oxygen 16, even though oxygen 16 is stable. Instead, it breaks apart at the point of absorbing the proton to make a helium nucleus and a carbon 12. Carbon-12 is where we started. So that's why it's the CNO cycle. We got back to where we started. What did we put in? We put in, I'm going to change the color here. Like the song says, 1, 2, 3, 4, no 5, 6 for him. 1, 2, 3, 4 protons, and out came a helium. So we didn't have to have 6 protons going in like we did before. This process is a little more efficient. It gives off a little more energy per 4 protons that are combined to make the helium. So why doesn't our sun do this? It's not massive enough to create that 20 million kelvins in the core that's necessary. So we're stuck with a lower efficiency. Okay, I'm going to end today by talking about convection. We've talked about convection. Convection is hotter things float up, colder things float down. We had on the test, I think, a question about granules being signs of convection. Why does convection occur in a star? If you have efficient heat transport, then you'll have temperature equilibration and you won't have convection. But if you have inefficient heat transport, that's if the heat's taking too long to transport, you'll get regions that are hotter than they should be for equilibrium. Because they're hotter than they should be for equilibrium, they'll start floating up. That's convection. So if you have efficient transport of energy, you don't have convection. But if you don't, then the convection kicks in. So it depends on the conditions in the star, the density of the material and whatnot, if you're going to have efficient transport of energy. So in our sun, where did we say we have convection? We see it in granules, that's our clue. Okay, up to the photosphere, but not in the core. But for smaller stars, you're going to have a more dense core, and it's going to start having convection down there. So you have convection in different locations in different mass stars because of the situations. So you look at this picture here, a very massive star, it has convection in the middle, not on the outside. This one here, like our sun, it has convection on the outside, not in the middle. This small star here has convection all the way through. That actually makes a difference to the star. You have convection all the way through, you're taking your fuel and running all of the fuel through the core. If you're like our sun and the convection is only in the outside, you're not bringing any new fuel into the core. And so what happens at death is going to be affected by if you had that complete convective mixing, as we call it, or not. And like I said, I'm going to stop here. And we'll pick up here next class period. Why am I stopping here? Because I want to pass out the test. I'm going to stop the recording here as well. No point in recording me handing out the test.